Okay, so we continue with what we started in the last lecture, that is, we started on orthogonal range searching, for which we defined two kinds of data structures, KD trees, which KD trees are actually very universal and very general, and then we described something called orthogonal range searching trees, which have a somewhat faster, not somewhat, substantially faster query time, but at the expense of a little bit of blow up in the space. And I mentioned that despite all that, in practice you would still prefer having something that is linear space, because space is an overhead that you have to carry all the time. And then I posed this problem of searching. So, given a set of points, if my query is not in axis aligned rectangle, but something that is infinite in one side. Okay, so it's a rectangle, let us say, which is where the top side is open essentially. So, this is infinity essentially, unbounded in this direction. Right. So, when you have this kind of queries, it is also called a three-sided query. And we can certainly use our orthogonal range searching data structure to support this query. So, there is no problem. Okay, I can always put a bound on the upper side, which is way above the set of points, and I can answer that query using the orthogonal range searching data structures, range trees. But the question here is that since this object is somewhat simpler, not too much simpler, so it is not as simple as So, you remember when I tried to explain, at least expose the idea of the range searching tree, we talked about an infinite slab in both directions. Okay, and that turned out to be kind of a one dimensional problem. But then I did not want to use the one dimensional solution. I actually use the KD tree solution to illustrate the use of this. How do you look upon this as a union of canonical intervals, right? So, this kind of query was handled using we built the range search tree, which is nothing but essentially look at these set of canonical intervals and sum up the queries that you come that you get from each of these individual disjoint slabs. Okay. So, the range search data structure should be viewed upon as a way where we take the x axis, okay, and we can take any interval in the x axis and express it as a union of the intervals expressed by some of the nodes, okay, and those are the ones that I am calling canonical intervals, and any interval can be expressed as a union of about 2 log n canonical intervals. This each of those intervals is represented by some kind of a node in the range search tree. Right. But here now I am actually not talking about the unbounded slab, but I am actually bounding the slab in one direction. And now I want to ask the question that can we do better than rectangular range query in terms of both space and query time. So, this is nothing but the query is x1 x2 Cartesian product with y1 infinity, sorry, y1 comma. So, more specifically, can we reduce the space to linear, and can we have the query time to something like order log n plus k? That is the question I am posing. And if you had some of you, I did some of you catch some of you in the weekend geometry school, and in one of the talks, I think Pankaj did make an allusion to something called this. What is the a way of searching where you can search in more than one sorted list by using a data structure technique called fractional cascading, right? So, if you use fractional cascading, so in fact fractional cascading historically, it was discovered in the context of answering rectangular range query, where the query time, so what we discussed last time, again just quickly recap. So, this is basically what we had proved, right? The range search trees gave us a log square n plus k query time and n log n space, right. So, it is possible to improve this one, this I can write on this. So, it is possible to improve this log square n to log n using fractional cascading. Right? It is just that the data structure becomes even more cumbersome. You have to build another layer of data structuring on that to reduce from log square n to log n, right? But it is possible. However, the space remains the same. So, when you use fractional cascading, so maybe I should just mention a word of fractional cascading again. So, if you the overall scheme or the overall technique of fractional cascading is quite general actually. So, the way we require it here is that we have a sequence of lists. So, if you look at the range search tree, the range could take some particular path in the tree, okay, and then we will do binary search in y direction, because here we are expressing some kind of interval using the primary range search tree, but within each node we keep the y coordinates sorted, right. So, within each node, if I blow up this node, okay, we keep the a one dimensional data structure where the points are sorted in the y direction, okay, so that you do a binary search or something similar to binary search, where you can answer each query in time proportional to log n plus the number of points inside, right. So, within each node we have this kind of a data structure, right. So, this and we are looking at about 2 log n nodes, okay, one for the right path, one for the left path. So, you end up doing this query on order log n nodes, and therefore, you get that log square n plus the number of points to be reported. Now, all these sorted lists that I maintain here, I have another sorted list here, okay, I have another sorted list here. So, if I can somehow combine the binary searches of this all the lists that occur in this path, okay, then and I spend, then what happens that, see, to locate the initial point you take log n time, after that you basically walk through and report the points. So, the initial binary search that is important, okay. So, if I am searching in k lists, okay, suppose we are searching in L lists, L sorted lists, okay. So, if we can do this in time order log n plus L, I claim that you can't hope to do anything better than this. So, I am just paying for one binary search, I have to do one search, I can't avoid that, okay. And somehow based on that information, I am able to locate my initial point in each of the lists. So, here also I am able to locate where I start from, here also I know where to start from, and I am paying only constant amount additional time for each sorted list. So, then and for in this particular context, the L is basically 2 log n, right. So, then your search time becomes order log n plus of course, the number of points reported. Number of points are reported only once, because we have ensured that the lists over the different levels are disjoint, So, no point is reported more than once. Even if it were it had been reported twice or thrice, it would still have been big O of that. Right. So, this is the way fractional cascading technique is used to combine binary search over over a whole I mean, so not just one list, but multiple lists. Right. And in general, since I brought up this topic, it is even more general. Actually, what one can do is you can have a underlying. So, there we are talking about a tree data structure, right. I mean, the primary data structure was tree, and the lists were basically the nodes of the tree. Okay. Now, you can think about this tree as a special kind of a graph, where the graph is a tree. Now, what happens if I have a graph structure, just an underlying graph structure? Okay. If I have an underlying graph structure, which can be anything, which could is not even necessarily an acyclic graph. I could have any kind of structure, okay, and I have not planar, not acyclic, nothing, some underlying graph structure, and then with each node, so let's call the vertices, V1, V2, V3, V4, etc. So, Vi has an associated node, sorted list, call it delta I. Okay. So, in this structure, and if you want to search in multiple lists. Okay. Now, the multiple lists, let us call them L prime 1, L prime 2, some L prime k. Now, the only restriction here is that L prime 1, L prime 2 all the way up to L prime k, they are not arbitrary nodes, but they are actually they form a connected subgraph. Okay. Well, connected subgraph essentially means a connected tree, because why should you have a subgraph, because if I search once in each node, that's sufficient. Okay. So, essentially the only restriction is that this form is subtree of. So, if I call this underlying graph G, they form a subtree of G. So, if I have this restriction that the set of nodes that we are going to search for, okay, is a subtree of the original graphical structure, okay, then we can apply this technique of fractional cascading, build some data structure on these, and you can get this kind of performance of log n plus k overall search time. Right. So, what are we doing? We have a common key to search, right. If you want to search for a common key alpha, the key is common, it is the same key that we are searching. So, when we search in multiple lists, of course, we are not searching for different keys, it is the same key that we are searching for, and we do not have to do independent binary searches. We can build a data structure on this underlying graph. These are also sometimes called catalogs. So, lists are also called catalogs. So, we can search through this whole set of catalogs. There are k catalogs, you can search in log n plus k time. Right? And this version of the fractional cascading is much more complicated than what happens in the trees, because in trees more or less the technique is that you merge these the lists of the of the lower most level with the and you take a fraction of those keys. It's like taking every other key and pushing it up, so that the gaps are not too much. So, you merge them basically, but at the same time you maintain the so one of course requirement here is that total size of data structure should not be superlinear. So, it should be order the sum of the size of the individual lists. So, fractional cascading achieves this logarithmic bound without blowing up the space too much. Okay. In the case of where the graph is a tree, it is rather simple, because we just take the lists of the lowermost level, merge it, take every alternate key, merge it, then of that we take every alternate, merge it. So, it is like a it's like a geometric series. So, overall the space remains linear. Okay. The challenge in a more general situation is that it's because there are actually going to be cycles. So that's just that selecting every other key is not going to work. So it becomes very complex. But there are some simpler solutions also based on randomization. So I don't want to discuss it too much here, but if someone is interested to follow it up, we'll be happy to give you pointers. Okay. So the only reason I mentioned this fractional cascading without getting into the details is many of these algorithms in for range searching and even for segment trees kind of data structures, whenever we have this log square n, in many cases we can actually pose it as a fractional cascading problem and reduce the log square n to log n, and the advantage is not so much in practice, log square n, log n, who cares really, but the real advantage or the real value of this is that theoretically you are able to match the optimal bounds. That is what is the real value of it. Okay. So fractional cascading is hardly used in practice because it's fairly complicated, but there is a simpler randomized construction for this. Okay, so let's get back again to this problem of priority search trees, where we have a somewhat restricted version of the rectangular query. We have a rectangle that is infinite in one direction. Okay. So, it is called this three-sided query, and the question we are asking is, can we do something better than what we achieved using the straightforward range search trees, that is from log square n, I want to bring it down to log n, and from the n log n space we want to get it down to order n. So, what is your gut feeling? Because I brought it up, surely something is possible, right? So, even before I get into this, let me make a very elementary observation about something some of you may be aware of, but I am not sure. It's something simple that often gets glossed over, or we don't pay enough attention to that. Right? So, I will pose a related but a simpler problem, and that is, so I am given a set of points and I want to pose the one dimensional problem, and I have my queries are let us say again semi intervals let us say infinity to x, right, infinity x, by which I mean basically I could get queries like this. Okay. So, this is my query. So, when I get this query, suppose these points are P1, P2, P3, P4, P5, P6, etc. So, for a query like this, the answer is P1, P2, P3, P4. Okay, it's a very simple one dimensional problem. There are so many methods of doing it, essentially again based on binary search. Right? But there is another way of solving it, and maybe you can just think about it for a moment. So, I claim that heaps can be used effectively, and why would we prefer heaps over? So, we could just basically sort the sequence and do the binary search and be done with it. Right? And I want to again achieve a query time of order log n plus k. That is my goal, linear space order log n plus k. So, why would we prefer, why would I even bring up this heap here?
Maybe you want to insert a delete point?
No, so I am talking about static data structures.
There is no additional cost for searching that, reaching that interval point. I mean, as and when we are moving down, we are reporting.
Yeah, but no, my first, you are already giving me the solution. So, solution probably is also obvious once I mention the heap, but why would I look for a heap? Why would I look for a heap based solution? What is the advantage of heap? something more fundamental.
First point is always
Yeah, yeah, yeah.
building time is linear.
Yeah, exactly, right. So, I do not have to sort, okay. I can build a heap in linear time. So, always remember this important distinction that between search trees and heap, okay. In terms of construction time, in heap you do not have to sort, it can be built in heapified in linear time, okay. So, wherever you are trying to really save time in the pre-processing, you can use heaps. Okay, and how would you use heaps here? What kind of heap would you like to use? So, some of you maybe know the solution, but okay. So, let me just so when you build a heap, again it's a conceptually like a complete binary tree, right. So, what kind of heap would you build on these points? Max, min, whatever. What? Okay. So, should I turn around the problem actually, because the way I posed the two-dimensional problem was the upper one was sorry, this is actually minus in, I'm sorry, we should turn it around because right this way it is increasing, right. So, then I should actually say x comma infinity, okay. So, sorry, so just lost its orientation. So, my semi intervals are like this. So, that way then we are saying min, but here you should probably use a max heap, right. So, the one with the highest coordinate, okay, should be here, right, and so on and so forth. And what is the advantage? If this point, so what are we going to do here? How are we going to search this heap? Say it again.
Keep on deleting the elements till you encounter.
Well, delete means what? We are not deleting, we are searching, right. So, we have built a heap on this set of points. Now, we get this query, this semi interval query. How are you going to answer the query?
Move down one level.
Right. So, first we compare whether this x is less than or sorry, greater than this element, right. We build a heap only on the x coordinates, okay. So, if x is greater than, okay, the root value, okay, then there is nothing to do really, right. I mean, no point can be within this interval, because this is the highest contains the highest value, and if my x exceeds that, if my interval is somewhere here, I obviously am not going to report any points, okay. So, only if x is less than this point, okay, then we will report this point, right, we will report the point, okay, and explore if there are more points to be reported, right. And now, here we are not going to walk along a single path, but we may have to branch both ways, because it is a heap. It is a heap. So, the next 2 points are something that again I am going to compare with the x, okay. Same strategy again. If the values here are smaller than x, then this entire subtree will have values smaller than x. So, I need not go down in the subtree at all, but it could be larger than x, in which case I again go down, and when I go down I have to try both paths, okay. So, overall what is the search time do I require for with a strategy like this? Say again. Order k, right. So, why is it order k? Yeah. So, when we stop at a node, okay, it basically means the value of the node, okay, is less than x. So, obviously, the subtree need not be looked into, all those points will be smaller than x, I did not look into it, but even this value may not be reported, okay. So, we may have visited this node, but not reported anything. See, we are the overall way this range searching works is that when we visit a node, it is like it is a charge, I encounter some charge because I am paying the cost of visiting the node. And if I report some point, then that cost is subsumed in reporting the point, because I am reporting a point. So, it is meaningful, or we have made a successful visit, that we have reported a point and we have paid some constant cost for that. But here it may happen that we visit this node and we do not report any point, okay. But then how many such nodes can be there where we do not report any point? Total of well, there are. So, see, this is the overall heap, let us say. Okay, we you can actually kind of argue that you may stop your search at some nodes when the depth will be some kind of maybe it is you go down a little bit more because it's a heap, maybe you go down more on this path than this path. So, you have stopped at all these vertices of the heap. Okay, and before this level you certainly reported something, otherwise you wouldn't have gone down to the level. So, what is the extra number of nodes that you visited where you did not report anything? At most twice the previous level, right. So, we are not going to visit more than the number of nodes where we do not report anything is no more than 2 times the number of points reported. Okay. So, that can be subsumed. So, therefore, it is order k, and the good thing about this is that we do not even have an additive log n term. Do you realize that? We did not even require that additional order log n term. So, when you do a binary search, you encounter that log n, and then of course, you walk and report the points. Here, I have actually been able to not only build the heap much faster, I have done it in linear time. My reporting is also only proportional to the number of points, and this is actually it's probably something that is surprising. You may not have expected this. Okay. So, heaps turn out to be a more effective data structure for one dimensional range searching. Okay. So, now we want to exploit this observation somehow. What do we have? Our problem at hand is so we have this set of points. And we have a query like this, some query. This is my 3-sided query, x1, x2, y1, this is infinity. So, I could, but this is a 2-dimensional problem. Okay, well, at least more than a 1-dimensional problem. If you use the range search tree, use the technique of the range search tree, again we should be thinking about splitting up this x1, x2 into some union of canonical intervals. Okay, we can put it through that tree and we will get union of canonical intervals. But we need to do something more clever to be able to achieve. So, at every level we are doing a binary search on the y, okay, and therefore, we encountered that log n plus log n plus the number of points reported and multiplied by the number of levels, we got that log square n. Right. So, can we somehow now combine the ideas of the heap and the range search tree? Heap at every node, again, see, we do not even want to have blow up the space. So, we do not want to have a heap at every node. See, one of the reasons the space blew up was there is a primary data structure and within the node there is another data structure, and somehow this summation of everything was not linear. So, we will have to combine, we will combine that heap and this thing, but we have to do it.
So give the heap with respect to y-axis because it's open in the
Right. So, we need the heap, from the way I have drawn this picture, we should think about a heap in the y direction, because in the y direction we have this semi interval, right. Heap in the y direction, okay, and some kind of idea about this range tree in the x direction. This range tree in the x direction may be better thought of as maybe the one dimensional KD tree actually. Maybe that is the better way of thinking about it, because KD tree is the one that gives you also this I mean the canonical intervals. So, whatever either you think about, maybe okay, maybe let's not confuse too much. So, range tree in the x direction and heap in the y direction, and we should store the points in a way such that a node should not contain more than constant number of points. Only then we can achieve the linear space. Okay. So, how do you do it? So, we have this this infinite, you know, it's like a well structure, right? So, if the point in this database are such that the highest of the y coordinate is lower than the bottom, then we do not need to search the data structure at all, right? We do not need to go any further if we find out that the value of y1, okay, is greater than the y max. The y max, let us say, is the y largest y coordinates among all the points.
So, if we solve the points on x and then make the heap on y,
yeah, we will do that. Effectively we will do that, yes. No, but when we do the heap on the y, I mean, how are you going to combine? The crucial question is, how are you going to combine the x and the y? See, the very fact that we are talking about a range tree in the x direction means that we will have them sorted in the x direction, no doubt about that.
Inside the heap, the points in the left we have x is less than the points in the
yeah, exactly. So, that is precisely what I am developing now. So, what I am claiming is the root of the tree or this data structure should contain the y max, the point having the that corresponds to the maximum y coordinate. Okay. So, you know, if in this set of points, maybe this is the point with the highest y coordinate. So, it is that whatever, you know, y prime y max or something. So, this one I propose we should make it the root of the tree. So, this one should be the root of the tree. Okay. Now, what we just articulated was, if okay, first thing we do while we do the range search is compare y1 with the y coordinate of this point. Okay. So, this point is that y prime x prime y max. We have stored that point here. So, I compare the y1 with y max. If y1 is greater than y max, obviously anything, because all the points whatever they are all smaller than y1, and so the output of the range search is an empty set. So, we do not need to go any further and look for points, right. We are done just on the basis of y, we are done, because the base itself is higher than the set of the points. Right. Fine, we may not be that lucky, but in some cases we did not go further, but this condition will hold for, we will try to make this condition hold for any node basically. If once we find that the base is has a larger x coordinate. So, for any subtree, suppose this is a tree like data structure, at any subtree, okay, we should have the largest y point with the largest y coordinate stored at the root. So, that we can always judge, we can always decide whether or not we should be searching that subtree. So, this kind of invariant will maintain all the time. Okay. Okay, after we have defined the root of the tree, now we do the division on the x side. Okay. So, we would like to actually achieve a kind of balanced tree. So, look at the median of the y coordinates, okay, and define. So, this is half, let us say the left half, call it L, left half based on y coordinates, x coordinates, and this is the right half again based on the y coordinates. So, this is the set of points. Okay. Now, do not compare the x coordinates with the x coordinate of this. No, x prime and this left half may not have any relation. Okay. This x prime y max, could be on one side of it. So, this one I am saying. So, this is already, let us see, to the right. Maybe it is also the rightmost point. Who knows? So, this point may not divide, this x coordinate may not divide the points equally into two halves. Okay. But I have stored it in the root. Okay. that point is gone. I don't need to. So, this point is not going to be considered for the further data structure. Okay. So, I have eliminated this point. Now, for the remaining points, I look at the median of the x coordinates, okay, and put and recursively we will construct the data structure. So, I have got the left half of points here and the right half of points here, and this does not include this point. Right. But what we will do in addition, in the root we have this point, we will also store the information about the median. Okay. So, what is the value? Maybe this is the median value, this point may have the median value, okay, x m or something like that. So, we will also store in addition to this some value x m. So, that we know that if x 1 is to the right of x m, we did not go and search these points at all, or if that x 2 is to the left of x m, we did not go and search this set of points. Okay. But in some cases we may end up, this x 1 x 2 may actually span the whole thing. So, x 1 x 2 may force us to take both the paths, that could also happen. Okay. So, the interval could actually get split either at this node and then recursively build the data structure for this set of points and this set of points using exactly the same observation. So, I will choose as the root of the left subtree the point with the highest y coordinate among all the points in the left tree. The root of the right subtree again will be the point that has the highest y coordinate among all the points in R, and that is how basically this tree is going to get built. And simultaneously you see that when I search, okay, like your range searching, this interval may get split at the root, or it may get moved to only one side, but at some point it may get split and something may be the forking node. So, it is like range searching, you know, it is going to move down on the basis of the x coordinates, but simultaneously we are not going to explore any subtree where we already know the node has a lower y coordinate than y 1. The moment we find that y 1 has a larger value than the y coordinate here, it means that all the other y coordinates are also lower, therefore, we do not explore that subtree. So, can you now tell me when we do the query? So, is that clear? The construction is clear? Okay. What is the space in the construction? A point is stored exactly once, right? Space is n. Point is stored exactly once. Fine. And implicitly we are sorting it, because every time we are finding the median, and therefore, in the end all the x coordinates, or at least we have ended up running our median on all these levels. So, we are kind of sorting the points. So, we have it is a little different because this point is taken out before it is sorted, right, but almost sorting point, maybe we are sorting half the number of points or something like that. So, it is certainly n log n and no more than n log n, right. So, pre-processing time is n log n, space is order n, because not only order n, each point is stored exactly once, of course, plus the whatever the tree, the tree itself will take some pointers. So, that is why order n. Now, what is the query time? That is the important thing. How many nodes are we going to visit? First of all, how many nodes are we going to?
The number of nodes we are going to report plus the number of x intervals there.
Okay. So, let us classify the nodes that we want to visit. Okay. We will visit a node, okay, if there are many situations where we visit a node. The y coordinate of the parent node v of the parent, let us say p of v, okay, had a larger y coordinate than y 1. That is why we went down. Y 1 was smaller than the y coordinate of the root. So, we went down to the two children. Okay. So, that is one reason why we may end up visiting a node.
Also, the
Yeah. So I'm just saying that. Okay, and so let me treat them separately. Actually, that can be treated at once, but let me just overcount it a little bit. Okay, or the median x of the parent, well median x of the tree rooted at the parent, right? Falls within the interval x1 x2, right. The median passes through somewhere here. So, the entire interval is not contained to one side. Okay. So, this is one thing, and there are of course some of these nodes. Okay. So, for some nodes we will report the point, okay, which are basically successful nodes, and there is no problem in charging it. The problem is for some nodes. So, for how many nodes we fail? You are saying 2k for the y coordinate. So, if there are k points to be reported from our analogy of the heap, okay, we can visit 2k. Good, that is a nice way of counting. So, you are looking at two kinds of failures on y and x, right. So, successful are the ones we do not need to bother about. Okay. So, failed nodes are of two kinds, one for the y and one for the x. Okay. So, for the y, what is being said is we can fail at most 2k, right, 2 times number of points reported by the same argument as the heap. Right. The parent reported something, therefore, we went down, okay. But it is not clear the parent should be reporting, right. Yeah, because there is also a y x component, right. So, the it could happen, very good, that is a good point. So, you have a situation like this, okay, where the y max is here, but this point itself may not be in sight. Okay. Yeah, so now it's slightly more tricky to count. Okay, your intuition is correct, you know. So how should we count then? So let's first look at the x then, maybe. How many nodes can we fail on as far as the x is concerned? Now use your range search tree thing. So we are visiting no more than 2 log n nodes in the x direction, right? Yeah. Right. Exactly. So so analogous to range searching, we visit at most 2 log n nodes. So, even whether we fail or not, you know, it can add at most log n such things or order log n such things. And I did not fully specify the search. So, this is how I was specifying the search. So, we should actually, you know, like any other range searching, if we find that, you know, for a subtree, the the range I am searching is split already, right. So, let us say, you know, this was what I was searching, and some point it split, and then now we are only looking at not only infinite in the y direction, we have also split this. So, we are actually looking at situation like this essentially, right. After the fork node, we are looking at situation like this, because the other part has gone to the fork node. Okay. So, once it has forked, the region is like this, and if this entire region is contained within the the interval spanned by this node is contained completely within, okay, then we need not go down this thing. Is the way that we define the canonical intervals, right? So, the interval denoted by this x interval denoted by this may be up to the here, okay, which is completely contained within this. Okay. So, we did not go down any further, and in the range search tree, what did we do? We stopped at this node. We did not want to go to the children node, but then we had to do a search in the y direction, because all the points in the subtree was also stored in this node. All the points in the subtree were stored in this node. Therefore, we could stop at this node. We could afford to stop at this node and do the y searching and report only those points that are contained within the y interval. Okay. Here, we are not storing all the points in this node. Okay. So, we may be forced to go down, because not all the points in the subtree are stored here. So, how do we know which points basically should be reported that lie within this region should be reported? Okay. So, we can't afford to stop there, we have to go down, but now we know that when we go down, we are only looking for a one dimensional range query, and now I use my heap, the analogy of the heap. I am only going to go down as long as I basically report points, and I am not going to sort of visit more than twice the number of points that I actually repeat. Right. So, now this whole thing, if you put this whole argument together, now we are basically visiting about order k, well, 2k nodes, but there is also this log n factor. Why would the log n factor be there? No, so there should be something in the y direction, right? After all, we are going to like the range search tree, we are going to express the y interval in terms of 2 log n canonical intervals. So, those log n I have to count anyway. So, those log n will get counted, okay. Plus, I am not going to do a binary search in these nodes. I am going to actually go down and report the points in, because they are stored as a heap also. Okay. So, I am going to visit 2 log n nodes like I do in the range search tree in the x direction, but when I report the points, I am not doing a binary search to report the points. I am only going down those subtrees, okay, which completely fall within, which basically define the canonical intervals, but within each of them I am only going to visit twice the number of points reported. So, overall then my analysis is, so search time. So, let us so this kind of argument where we decouple them is not is not the right thing to do. We can't look at them completely separately. I mean, things are happening actually together. So, overall, okay, there are 2 log n canonical intervals, okay, corresponding to some nodes, and within each of these canonical interval, let us think about the subtree of these canonical intervals. Within each of these subtree, I am not going to visit more than twice the number of points, right. So, we will descend from those nodes, okay, to some nodes, let us call it some n's of v. So, node n's of v till we find suitable y coordinates, and this is no more than twice the number of points reported. So, the overall search time becomes order log n plus k. So, we are never doing that sort of binary search in the y direction, that is why we are saving. And because we are not doing that binary search in the y direction, we are not encountering that log n cost for each of these canonical intervals. The heaps are buying us things, because in a heap we can do the semi-interval range query, range search, range reporting in order k time. That is all. Okay. And the point is being stored only once, so that is the space is order n. Okay. So, we have got the ideal bound that we are looking for. So, any questions or? Yeah, so it is a very clever data structure, and it is actually can be used in practice, because there is no complication as such. I mean, this is a little bit of a conceptual thing, but in terms of implementation is very clean. So, priority search trees are actually quite frequently used in many situations. Okay, so we will stop here today.